1955. Princeton, New Jersey. A man agonizes on his deathbed. In his final hours, he feverishly scribbles equations on scraps of paper. His eyes, those same eyes that saw beyond the veil of reality, now struggle to stay open. Albert Einstein is dying. But there is something that torments him. Something he discovered about the universe, something so disturbing that he himself doubted whether humanity was ready to understand. That man with rebellious hair was not just a scientist. He was a seer, an architect of the impossible, and what he built changed everything. Because Einstein didn't discover the universe. He proved that the universe was never what we thought. For centuries we lived in a comfortable illusion. Space? An empty, static stage where stars danced. Time? A universal metronome, ticking at the same rhythm for everyone, everywhere. Isaac Newton had built this cathedral of certainties, and the world slept peacefully under its roof. People looked at the night sky and saw order, predictability, a cosmic machine perfectly calibrated where each gear turned in eternal harmony. Astronomers mapped the stars as cartographers map continents, believing that the stage where these celestial lights shone was fixed, immutable, absolutely reliable. But something was wrong. Small anomalies began to appear in observations. Mercury's orbit behaved strangely, deviating slightly from Newtonian predictions. Light seemed to have a constant speed. No matter how you measured it, something that simply made no sense within the established framework. These were cracks in the edifice of certainty, almost imperceptible fissures that most scientists preferred to ignore or explain with complex adjustments to existing equations. Until Einstein awoke. And when he awoke, the world would never be the same. In 1915, Einstein published something humanity was not prepared to accept. His field equations of general relativity were more than advanced mathematics. They were a revolutionary declaration about the very nature of reality. Space and time, he affirmed, are not separate entities. They are not stage and clock. They are the fabric, the very substance of reality. And this fabric can be bent, stretched, torn. Imagine for a moment that everything you know about your position in the universe is wrong. You think you're sitting in a chair, in a room, on a planet that orbits a star. But Einstein said something much stranger. You are not in a place in space. You are on a wave in the ocean of spacetime, surfing an invisible geometry that determines not only where you are, but when you are. Think of it this way. Take a bed sheet and stretch it with 4 people holding the corners. This sheet represents the fabric of spacetime. Now place a bowling ball in the center. What happens? The fabric sinks, creates a depression, a curvature. Now roll a marble near the bowling ball. The marble won't go in a straight line. It will curve its trajectory, attracted not by a mysterious force, but simply following the geometry of the curved fabric. That is gravity, not an invisible force that pulls things through empty space, as Newton thought, but the curvature of spacetime itself. The sun doesn't attract the Earth with some magical force that acts at a distance. The sun, with its colossal mass of 1 masse, 989,000 kilograms, sinks the trampoline of the cosmos, and the Earth. It simply rolls through the depression that the sun creates, following the shortest path through a space that is no longer flat. Gravity is not a force. Gravity is geometry. This revelation was so profound, so absolutely revolutionary, that even today, more than a century later, our minds still struggle to truly absorb it. But here's what will blow your mind. Einstein didn't just reformulate physics. He predicted things that seemed too absurd to exist, things that even he himself, in his scientific caution, refused to completely believe, and all, absolutely all, proved to be real. The universe, in its infinite complexity, confirmed each of the predictions of that wild-haired man who worked in a patent office in Switzerland. The first prophecy came in 1919. A rare cosmic event was needed to test it. A total solar eclipse. When the moon passed in front of the sun on May 29 of that year, teams of astronomers positioned themselves at strategic locations around the world, one in Sobral, Brazil, another on Principe Island in West Africa. They pointed their telescopes not at the eclipsed sun, but at the stars that should be hidden behind it, blocked by the giant mass of our star. And they were there, visible. Displaced from their known positions. The sun's gravity was bending light exactly as Einstein had predicted 4 years earlier. The light from distant stars, traveling through the cosmos in a straight line for thousands of light years, encountered the curvature of spacetime created by the sun and changed direction. The universe had become a giant lens. The news traveled around the world. Revolution in science, proclaimed the newspapers. Newtonian ideas overthrown, new theory of the universe. Overnight, Einstein became a global celebrity, the face of human genius. But the implications of this discovery were far greater than one man's fame. If light could be bent by gravity, then entire galaxies could act as natural telescopes. A massive galaxy between us and a distant object could bend and amplify the light from that object, allowing us to see things that would otherwise be invisible. These gravitational lenses were not just theoretical curiosities, they were practical tools for exploring the cosmos. Today, the James Webb Space Telescope uses this Einsteinian magic to peer at galaxies formed when the universe was only 300 million years old. It is seeing through 13 billion years of curved spacetime, using intermediate galaxies as giant cosmic magnifying glasses. Without Einstein, without his understanding of how mass distorts the fabric of reality, we would be blind to the most remote epochs of creation. Every deep field image that Webb captures is a validation of equations scribbled by Einstein more than a century ago. But Einstein's second prophecy was even more disturbing. The field equations of general relativity, when taken to their logical extreme, screamed a truth that seemed like a science fiction nightmare. If you compress enough mass into a small enough space, the fabric of spacetime doesn't just curve, it tears. Gravity becomes so extreme, the curvature so sharp, that not even light can escape. A hole in reality, a place from which nothing returns. Einstein hated this idea. In 1939, he even published a paper trying to prove that such objects could not exist in nature. Nature cannot be so absurd, he wrote, convinced that some physical mechanism would prevent the complete gravitational collapse of a massive star. Nature responded, "Watch this." Just a few months after Einstein's death in 1955, the first quasars began to be detected, objects of unimaginable brightness in the far reaches of the universe. It took years for astronomers to understand what they were seeing, entire galaxies being devoured by supermassive black holes at their centers, releasing energy equivalent to trillions of stars. Today we know there is a supermassive black hole at the center of every galaxy, including ours. Sagittarius A, pronounced Sagittarius A star, resides in the heart of the Milky Way. It has 4 million times the mass of the Sun, compressed into a region of space smaller than Mercury's orbit. It's there, silently conducting the dance of 200 billion stars, including ours. In May 2022, astronomers revealed the first direct image of Sagittarius A, showing the characteristic ring of light emitted by superheated material spinning around the event horizon, the boundary beyond which not even light escapes. It's impossible to overstate how bizarre this is. There exists an object at the center of our galaxy where the normal rules of physics collapse, a place where time almost stops, where space curves infinitely upon itself, where density approaches infinity. A place that Einstein predicted mathematically but refused to accept philosophically. And black holes are not rare. Estimates suggest there are about 100 million black holes just in our galaxy, the remnants of massive stars that collapsed under their own weight. The universe is dotted with these wounds in the fabric of spacetime, silent validations of Einstein's equations. But perhaps Einstein's most extraordinary prophecy was that of gravitational waves. In 1916, just 1 year after publishing General Relativity, he calculated that violent events in the cosmos, collisions of black holes, mergers of neutron stars, supernova explosions, would not only distort spacetime locally, but would send ripples through the very fabric of the universe. Tremors in the structure of reality, traveling at the speed of light. The idea was, even by Einstein's standards, almost incomprehensible. These waves would be so weak that detecting them would be like measuring the width of a human hair on the scale of the entire distance between Earth and the nearest star. The scientific community, though impressed with the mathematics, considered the prediction impossible to verify. Too small to measure, they concluded. We will never detect them. Einstein, characteristically, was not certain. At different times in his life, He doubted whether gravitational waves were real or just mathematical artifacts of his equations. It was a question that would remain unanswered throughout his lifetime. But the search began. Decades after his death, scientists began building increasingly sensitive detectors. The project culminated in LIGO, the Laser Interferometer Gravitational Wave Observatory, a pair of L-shaped detectors, each arm 4 kilometers long, located in Louisiana and Washington, separated by 3,000 kilometers. The principle was simple, but the execution was almost absurdly complex. If a gravitational wave passed through Earth, it would compress space in one direction and stretch it in another. LIGO was designed to measure changes smaller than 1,000th the diameter of a proton. September 14, 2015. 5 hours and 51 minutes in the morning, Brasilia time. LIGO's 2 detectors, separated by 3,000 kilometers, captured exactly the same signal with a difference of only 7 milliseconds, the time it took for the wave to travel from one detector to the other. The signal lasted only 1/5 of a second, but in that brief moment, humanity witnessed something extraordinary. 1,300,000,000 years ago, when life on Earth consisted only of single-celled organisms floating in primordial oceans, 2 black holes, one with 29 times the Sun's mass, the other with 36 times, completed a mortal dance that had lasted millions of years. Spinning faster and faster, closer and closer, they finally collided and merged into a single black hole of 62 solar masses. But wait, 29 plus 36 is 65, not 62. What happened to the remaining 3 solar masses? They were converted into pure energy, the energy of a gravitational wave that tore through the fabric of spacetime. For a fraction of a second, that collision released more energy than all the stars in the observable universe combined. That energy traveled through the cosmos in the form of ripples in spacetime itself, crossing galaxies, galactic clusters, the intergalactic void. 1,300,000,000 years later, when humanity had already evolved, built civilizations, developed science, and created incredibly sensitive detectors, that wave reached Earth. It passed through you, through me, through all of us, compressing and stretching space by an unimaginably small fraction. Most of humanity noticed nothing, but LIGO noticed. The discovery was announced in February 2016 at a press conference that echoed the 1919 one that confirmed the bending of light. Scientists with tears in their eyes described what they had detected. A century after his prediction, the universe had confirmed Einstein once again. In 2017, 3 physicists won the Nobel Prize for this discovery. Since then, LIGO and its partner detectors, Virgo in Italy, Kagra in Japan, have detected dozens of gravitational waves. Each detection is a window into violent cosmic events, a new way to hear the universe instead of just seeing it. Astronomers now speak of multi-messenger astronomy, combining traditional light with gravitational waves to obtain a complete understanding of cosmic events. But Einstein's legacy is not just in distant telescopes and gravitational wave detectors. It's in your pocket. Right now, as you read these words, 31 GPS satellites are orbiting Earth at 20,000 kilometers altitude. Each satellite carries atomic clocks precise to the nanosecond, constantly sending time signals. Your phone receives these signals and, comparing the arrival times from multiple satellites, calculates your exact position on Earth's surface. But there's a problem. Up there, at 20,000 kilometers altitude, where Earth's gravity is weaker, time passes faster. Einstein predicted this with his general relativity. The weaker the gravity, the faster time flows. The difference is minuscule, only 38 microseconds per day. Seems irrelevant, right? Wrong, absurdly wrong. Light and radio signals travel at 300,000 kilometers per second. In 38 microseconds, a signal travels 11 kilometers. Without relativistic correction, without adjusting the satellites' clocks to compensate for the difference in time flow predicted by Einstein, your GPS would err by 10 kilometers per day. In a week, it would be completely useless. Every time you ask for directions, every time you request a taxi, every time you check your location on a map, you are using Einstein's equations. He is navigating you through a world he never knew, using a theory he developed to understand black holes and the cosmos, applied to practical, everyday problems. And it's not just GPS. General relativity is essential for understanding global positioning systems, telecommunications synchronization, even the functioning of the modern internet. The Einsteinian physics that began as a purely theoretical question, how does the universe really work, became the technological foundation of our connected civilization. Einstein transformed our understanding not just of the cosmos, but of reality itself. Before him, we thought space was an empty box where things happened, and time was a universal clock that ticked uniformly for everyone. After him, we understand that spacetime is a dynamic ocean, curving and rippling in response to matter and energy, creating the illusion of what we call gravity. He showed us that there is no universal now. Two events that are simultaneous for one observer may not be for another if they are moving relative to each other. Time is relative. Space is relative. Only the speed of light is absolute, unchangeable, a cosmic speed limit built into the very structure of the universe. He showed us that mass and energy are interchangeable, expressed in science's most famous equation, E=mc². This simple equation explains why the sun shines, transforming 4 million tons of mass into energy every second. It explains how nuclear power plants and atomic bombs work. It explains why nothing with mass can travel at the speed of light. The required energy would be infinite. He showed us that the universe has a structure, a geometry that can be measured, mapped, understood. Modern cosmologists use Einstein's equations to model the evolution of the universe from the Big Bang to the present, predicting its distant future. The same equations describe both the movement of planets and the expansion of the cosmos itself. But perhaps Einstein's most profound legacy is epistemological, about how we know what we know. He demonstrated that pure mathematics, careful theoretical thinking, can reveal truths about the universe that no amount of casual observation would reveal. He saw black holes, gravitational lenses, and gravitational waves not with telescopes, but with equations, decades before any observational evidence. At the same time, he insisted that physics should be testable, that theories should make verifiable predictions. His theories only gained acceptance because his predictions about the bending of light, Mercury's precession, time dilation, were confirmed by experiments and observations. He married deep theoretical thinking with rigorous empirical verification, setting the standard for how science should work. Einstein also personified intellectual courage. He was willing to question the most fundamental assumptions about reality, concepts like absolute space and absolute time that seemed obvious and unquestionable. He was willing to follow his equations to conclusions that he himself found uncomfortable, like black holes. He was willing to admit when he was wrong, as when he inserted the cosmological constant into his equations to force a static universe, only to remove it later when Edwin Hubble discovered that the universe is expanding. The biggest mistake of my life, Einstein supposedly called it, though ironically the cosmological constant has resurfaced in modern cosmology as the dark energy that accelerates the universe's expansion. He worked in relative isolation during much of his career, often against the mainstream of scientific thought. When he developed special relativity in 1905, he was a patent office clerk in Bern, without access to university libraries or academic colleagues. When he developed general relativity, he worked essentially alone for almost a decade, struggling with the complex mathematics of differential geometry. And yet, even in his solitary genius, Einstein recognized that he was building on the shoulders of giants. He revered Newton, even while reformulating Newton's gravitational theory. He collaborated with mathematicians like Marcel Grossmann, who introduced him to the mathematical tools necessary to express his ideas. He debated vigorously with colleagues like Niels Bohr about interpretations of quantum mechanics, even when they didn't reach agreement. Einstein's personal story is as fascinating as his scientific contributions. Born in Ulm, Germany, in 1879, he showed early talent for mathematics, but was a rebellious student who questioned authority. He dropped out of German high school, considering it too rigid, and moved to Switzerland. He had difficulty finding academic employment after graduation, apparently because his professors disliked his independent behavior. It was in the patent office, examining proposals for time synchronization devices, that he began to think deeply about the nature of time and simultaneity, reflections that would lead to special relativity. His miracle year of 1905 saw the publication of 4 revolutionary papers, each worthy of a Nobel Prize, on the photoelectric effect, Brownian motion, special relativity, and mass-energy equivalence. Even so, it took years for academia to recognize his genius. He continued working in the patent office until 1909. His first university position was in Zurich. He passed through Prague and returned to Zurich before finally accepting a position in Berlin in 1914, where he developed general relativity while World War I devastated Europe around him. The confirmation of light bending in 1919 transformed him into a global celebrity, but also made him a target. As a German Jew promoting Jewish physics in an era of rising anti-Semitism, he faced hostility and even death threats. When Hitler came to power in 1933, Einstein was visiting the United States. He decided not to return, settling at the Institute for Advanced Study in Princeton, where he would spend the last 22 years of his life. In these final years, Einstein became a figure of contradictions. He was the father of modern physics, but increasingly uncomfortable with what quantum physics revealed about the nature of reality. God does not play dice, he famously declared, rejecting the probabilistic interpretation of quantum mechanics favored by Bohr and others. He spent decades searching for a unified field theory that would reconcile relativity and quantum mechanics, but never succeeded. He was a convinced pacifist, but signed the letter to President Roosevelt in 1939 warning about the possibility of Nazi nuclear weapons, a letter that helped launch the Manhattan Project. He vehemently opposed the use of the atomic bomb against Japan and spent his last years advocating for nuclear disarmament and world government. He was a deep thinker on social and political issues, defending civil rights, criticizing American racism, supporting cultural Zionism, while opposing Jewish nationalism. His political views were nuanced and evolved over time, reflecting the same independent thinking that characterized his science. And personally, he was complex and flawed. His marriages were troubled. He was an absent father to his children. He could be charming and warm, but also distant and absorbed. He was deeply human in his contradictions, reminding us that scientific genius does not equal personal perfection. When Einstein died on April 18, 1955, from a ruptured abdominal aortic aneurysm, he refused surgery. "I want to go when I want," he said. "It is tasteless to prolong life artificially. I have done my share. It is time to go. I will do it elegantly." In his last hours, he was still working on equations, seeking until the end that elusive unified theory. His body was cremated and his ashes scattered in an undisclosed location, following his wishes not to have a burial place that could become a pilgrimage site. But his brain was removed during the autopsy, without his family's permission, by pathologist Thomas Harvey, who preserved and studied it, looking for physical clues to genius. Decades later, some studies suggested minor structural differences, but nothing conclusive. Einstein's genius resided not in anatomical quirks, but in his extraordinary capacity for abstract thinking, visualization, and mathematical insight. His scientific legacy continues to grow. General relativity has passed all experimental tests with remarkable precision. Observations of binary pulsars showed exactly the energy loss through gravitational waves that Einstein predicted. Experiments with atomic clocks on airplanes confirmed gravitational time dilation. Particle colliders regularly convert energy into mass and vice versa, validating each upwind-set of Gachoclaf. This is an vice the opposite of an fostais and from Ponsens. The Gravity Probe B satellite confirmed subtle effects of general relativity, such as the dragging of spacetime by a rotating object. And new applications continue to emerge. Astronomers use gravitational lenses to map the distribution of invisible dark matter in the universe. Physicists study gravitational waves to test theories of quantum gravity and explore extreme conditions impossible to replicate in the laboratory. Engineers use relativistic corrections in everything from satellite navigation systems to communication network synchronization. Einstein transformed astronomy from a science of observing points of light into a science of understanding the geometry of the universe. He showed us that the cosmos is strange, elastic, and incredibly connected, that space is not empty but alive, responding to the presence of mass and energy. That time is not absolute but malleable, flowing at different rates depending on gravity and motion. That matter and energy are two faces of the same coin. that the universe has a history. It was born in a Big Bang about 13,800,000,000 years ago, expanded and cooled, formed stars and galaxies, and continues to evolve. Before Einstein, we didn't have the conceptual or mathematical language to ask these questions, much less answer them. After Einstein, cosmology became a precise science. We can measure the age of the universe, its expansion rate, its composition. We know that normal matter, protons, neutrons, electrons, constitutes only about 5% of the universe. The rest is dark matter and dark energy, mysterious substances that interact mainly through gravity, detectable only by their gravitational effects described by Einstein's equations. We know we live in a universe that began infinitely hot and dense and cooled as it expanded. We know the first stars formed about 100 million years after the Big Bang, forging heavy elements in their cores and scattering them through the cosmos when they exploded as supernovas. We know our sun is a third-generation star, formed from recycled material from earlier generations of stars. We know that every atom in our bodies, except hydrogen, was forged in the core of a star or in a supernova explosion. We are literally stardust. And we know all this because Einstein gave us the tools to understand how gravity works on cosmic scales. His theory is not just a mathematical description, it is a profound insight into the nature of reality, a glimpse of the underlying structure of the cosmos. That man who died in 1955, scribbling equations until the end, left a gift to humanity, proof that the universe is far stranger, more beautiful and more connected than we ever dared to dream. He showed us that reality itself is richer and more surprising than our everyday intuition suggests. That common sense, formed by our experience on a small planet spinning around a common star, is not a reliable guide to the fundamental nature of the cosmos, and every time we look at the night sky, we are not just seeing light, we are seeing the geometry of creation written in the equations of a man who learned to read the universe's handwriting. We are seeing photons that have traveled millions or billions of years through curved space. We are looking back in time because light has finite speed. We are witnessing the universe as it was, not as it is. Einstein's legacy reminds us that human curiosity, rigorous thinking, and the courage to question the obvious can reveal profound truths about our existence. That an individual, armed only with paper, pen, and powerful imagination, can forever change how humanity understands its place in the cosmos. That the most abstract and apparently impractical questions, what is time? What is space? How does gravity work? Can have answers that transform our civilization. Einstein proved that the universe is comprehensible, that nature operates according to mathematical principles we can discover and understand. In a cosmos of impossible dimensions, of scales ranging from the subatomic to the supergalactic, of phenomena that defy intuition, there is still order, there is logic, there is mathematical beauty. And the human mind, however limited it may be, can capture at least a glimpse of that order. This is perhaps Einstein's most profound lesson, that the universe is both stranger and more wonderful than we imagined, and that we have the capacity, perhaps even the obligation, to explore it, question it, understand it. That imagination, as Einstein said, is more important than knowledge. Because knowledge is limited to what we know now, but imagination embraces the entire universe and everything we will ever know.